A Brief History of Time, written by Stephen Hawking, read by Akashvi. Hello and welcome to the world of cosmos. Today I'm reading Stephen Hawking's book, A Brief History of Time. This is the fifth video, chapter number 5, Elementary Particles and the Forces of Nature. Aristotle believed that all the matter in the universe was made up of four basic elements: earth, air, fire, and water. These elements were acted on by two forces: gravity, the tendency for earth and water to sink, and levity, the tendency for air and fire to rise. This division of contents of the universe into matter and forces is still used today. Aristotle believed that matter was continuous. That is, one could divide a piece of matter into smaller and smaller bits without any limit. One never came up against a grain of matter that could not be divided further. A few Greeks, however, such as Democritus, held that matter was inherently grainy and that everything was made up of large numbers of various different kinds of atoms. The word atom means indivisible in Greek. For centuries, the argument continued without any real evidence on either side. But in 1803, the British chemist and physicist John Dalton pointed out that the fact that chemical compounds always combine in certain proportions could be explained by the grouping together of atoms to form units called molecules. However, the argument between two schools of thought was not finally settled in favor of the atomists until the early years of this century. One of the important pieces of the physical evidences was provided by Einstein in a paper written in 1905, Spatial Relativity. Einstein pointed out that what was called Brownian motion, the irregular random motion of small particles of dust suspended in a liquid, could be explained as the effect of. By this time, there were already suspicions that these atoms were not, after all, indivisible. Several years previously, a fellow of Trinity College, Cambridge, J. Thomson, had demonstrated the existence of a particle of matter called the electron that had a mass less than 1/1000th of that of the lightest atom. He used a setup rather like a modern TV picture tube. A red-hot metal filament gave off the electron, and because these have a negative electric charge, an electric field could be used to accelerate them towards a phosphor-coated screen. When they hit the screen, flashes of light were generated. Soon it was realized that these electrons must be coming from within the atoms themselves. And in 1911, the British physicist Ernest Rutherford finally showed that the atoms of matter do have internal structure. They are made up of an extremely tiny positively charged nucleus, around which a number of electrons orbit. He deduced this by analyzing the way in which alpha particles, which are positively charged particles given off by the radioactive atoms, are deflected when they collided with atoms. At first, it was thought that the nucleus of the atom was made up of electrons and different numbers of positively charged particles, called the proton, from the Greek word means first. However, in 1932, a colleague of Rutherford's at Cambridge, James Chadwick, discovered that the nucleus contained another particle called the neutron, which had almost the same mass as a proton but not electrical charge. Chadwick received the Nobel Prize for his discovery and was elected Master of Gonville and Caius College, Cambridge, the college of which I am now a fellow. This is said by Stephen Hawking. He later resigned as master because of disagreement with the fellows. He had been a bitter dispute in the college ever since a group of young fellows returning after the war had voted many of the old fellows out of the college offices they had held for a long time. This was before my time. I joined the college in 1965 at the tail end of the bitterness, when similar disagreement forced another Nobel Prize-winning master, Sir Neville Mott, to resign. Up to about 20 years ago, it was thought that protons and neutrons were elementary particles, but experiments in which protons were collided with other protons or electrons at high speeds indicated that they were in fact made up of smaller particles. These particles were named quarks by Catholic physicist Murray Gell-Mann, who won the Nobel Prize in 1969 for his work on them. The origin of the name is an enigmatic quotation from James Joyce, 3 quarks for Mr. Mark. The word quark is supposed to be pronounced like quartz, but with a k at the end instead of a t, but it is usually pronounced to rhyme with lark. There are a number of different varieties of quartz. There are thought to be at least 6 flavors, which we call up, down, strange, charmed, bottom, and top. Each flavor comes in 3 colors: red, green, and blue. It should be emphasized that these terms are just labels. Quarks are much smaller than the wavelength of visible light and so do not have any color in the normal sense. It is just that modern physicists seem to have more imaginative way of naming new particles and phenomena. They no longer restrict themselves to Greek. A proton or neutron is made up of 3 quarks, 1 of each color. A proton contains 2 up quarks and 1 down quark. A neutron contains 2 down and 1 up. We can create particles made up of the other quarks: strange, charmed, bottom, and top, but these all have a much greater mass and decay very rapidly into protons and neutrons. We now know that neither the atoms nor the protons and neutrons within themselves are indivisible. So the question is, what are the truly elementary particles, the basic building blocks from which everything is made? Since the wavelength of light is much larger than the size of an atom, we cannot hope to look at the parts of an atom in the ordinary way. We need to use something with a much smaller wavelength. As we saw in the last chapter, quantum mechanics tells us that all particles are in fact waves, and that the higher the energy of a particle, the smaller the wavelength of the corresponding wave. So, the best answer we can give to our question depends on how high a particle energy we have at our disposal, because this determines on how small a length scale we can look. These particle energies are usually measured in units called electron volts. In Thomson's experiments with electrons, we saw that he used an electric field to accelerate the electrons. The energy that an electron gains from an electric field of 1 volt is called, or is known as, an electron volt. In the 19th century, when the only particle energies that people knew how to use were the low energies of a few electron volts generated by chemical reactions such as burning, it was thought that atoms were the smallest unit. In Rutherford's experiments, the alpha particles have energies of millions of electron volts. More recently, we have learned how to use an electromagnetic field to give particles energies of at first millions and then thousands of millions of electron volts. And so, we know that particles that were thought to be elementary 20 years ago are in fact made up of smaller particles. May these we go to still higher energies, in turn be found to be made up of still smaller particles. This is certainly possible, but we do have some theoretical reasons for believing that we have or are very near to a knowledge of the ultimate building block of nature. Using the wave-particle duality discussed in the last chapter, everything in the universe, including light and gravity, can be described in terms of particles. These particles have a property called spin. One way of thinking of spin is to imagine the particle as little tops spinning about an axis. However, this can be misleading because quantum mechanics tells us that the particles do not have any well-defined axis. What the spin of a particle really tells us is what the particle looks like from different directions. A particle of spin 0 is like a dot. It looks the same from every direction. On the other hand, a particle of spin 1 is like an arrow. It looks different from different directions. Only if one turns it round a complete revolution 360 degrees does the particle look the same. A particle of spin 2 is like a double-headed arrow. It looks the same if one turns it round half a revolution, 180 degrees. Similarly, higher spin particles look the same if one turns them through smaller fractions of a complete revolution. All these seems fairly straightforward, but the remarkable fact is that there are particles that do not look the same if one turns them around just one revolution. You have to turn them through 2 complete revolutions. Such particles are said to have spin half. All the known particles in the universe can be divided into 2 groups: particles of spin half, which make up the matter in the universe, and the particles of spin 0, 1 and 2, which we shall see give rise to forces between the matter particles. The matter particles obey what is called Pauli's exclusion principle. This was discovered in 1925 by an Austrian physicist, Wolfgang Pauli. He was the archetypal theoretical physicist. It was said of him that even his presence in the same town with Pauli's exclusion principle says that 2 similar particles cannot exist in the same state. That is, they cannot both have the same position and the same velocity within the limits given by the uncertainty principle. The exclusion principle is crucial because it explains why matter particles do not collapse to a state of very high density under the influence of all forces produced by the particles of spin 0, 1 and 2. If the matter particles have very nearly the same positions, they must have different velocities, which means that they will not stay in the same positions for long. If the world had been created without the exclusion principle, quarks would not form separate well-defined protons and neutrons, nor would these together with electrons form separate well-defined atoms. They would all collapse to form a roughly uniform dense soup. A proper understanding of the electron and other spin minus half particles did not come until 1928, when a theory was proposed by Paul Dirac, who later was elected to the Lucasian Professor of Mathematics at Cambridge, the same professorship that Newton had once held and that I now hold. Dirac's theory was the first of its kind that was consistent with both quantum mechanics and the special theory of relativity. It explained mathematically why electron had spin half, that is, why it did not look the same if you turn it through only one complete revolution, but did if you turn it through 2 revolutions. It also predicted that the electron should have a partner, an anti-electron or positron. The discovery of the positron in 1932 confirmed Dirac's theory and led to his being awarded the Nobel Prize for Physics in 1933. We now know that every particle has an antiparticle with which it can annihilate. In case of the force-carrying particle, the antiparticle are the same as the particle themselves. There could be whole anti-world and anti-people made out of antiparticles. However, if you meet your anti-self, don't shake hands. You would both vanish in a great flash of light. The question of why there seem to be so many more particles than antiparticles around us is extremely important, and I shall return to it later in the chapter. In quantum mechanics, the forces or interactions between matter particles are all supposed to be carried by particles of integer spin 0, 1 or 2. What happens is that a matter particle such as the electron or a quark emits a force-carrying particle. The recoil from this emission changes the velocity of the particle matter. The force-carrying particle then collides with another matter particle and is absorbed. This collision changes the velocity of the second particle, just as if there had been a force between the two matter particles. It is an important property of force-carrying particle. It is an important property of the force-carrying particles that they do not obey the exclusion principle. This means that there is no limit to the number that can be exchanged, and so they can give rise to a strong force. However, if the force-carrying particle have a high mass, it would be difficult to produce and exchange them over a large distance. So, the forces that they carry will have only a short range. On the other hand, if the force-carrying particle have no mass of their own, the forces will be long range. The force-carrying particles exchanged between matter particles are said to be virtual particles because, unlike real particles, they cannot be directly detected by a particle detector. We know they exist, however, because they do have a measurable effect. They give rise to a force between matter particles. Particles of spin 0, 1 or 2 do also exist in some circumstances as real particles when they can be directly detected. They then appear to us as what a classical physicist would call waves, such as waves of light or gravitational waves. They may sometimes be emitted when matter particles interact with each other by exchanging virtual force-carrying particles. For example, the electric repulsive force between two electrons is due to the exchange of virtual photons, which can never be directly detected. But if one electron moves past another, real photon may be given off, which we detect as light waves. Force-carrying particles can be grouped into 4 categories according to the strength of the force that they carry and the particles with which they interact. It should be emphasized that this division into 4 classes is man-made. It is convenient for the construction of partial theories, but it may not correspond to anything deeper. Ultimately, more physicists hope to find a unified theory that will explain all 4 forces as different aspects of a single force. Indeed, many would say that this is the prime goal of physics today. Recently, successful attempts have been made to unify 3 of the forces categorized, and I shall describe these in this chapter. The question of the unification of the remaining category, gravity, we shall leave till later. The first category is the gravitational force. This force is universal. That is, every particle feels the force of gravity. According to its mass or energy, gravity is the weakest of the 4 forces by a long way. It is so weak that we would not notice it at all were it not for two special properties that it has. It can act over large distances, and it is always attractive. This means that the very weak gravitational forces between the individual particles in two large bodies such as Earth and the Sun can all add up to produce a significant force. The other three forces are either short range or are sometimes attractive and sometimes repulsive. So they tend to cancel out. In the quantum mechanical way of looking at the gravitational field, the force between two matter particles is pictured as being carried by a particle of spin 2 called the graviton. This has no mass of its own, so the force that it carries is long range. The gravitational force between the Sun and the Earth is ascribed to exchange of gravitons between the particles that make up these two bodies. Although the exchanged particles are virtual, they certainly do produce a measurable effect. They make the Earth orbit around the Sun. Real graviton make up what classical physicists would call gravitational waves, which are very weak and so difficult to detect that they have never yet been observed. The next category is the electromagnetic force, which interacts with electrically charged particles like electrons and quarks, but not with uncharged particles such as gravitons. It is much stronger than the gravitational force. The electromagnetic force between two electrons is about a millions, one with 42 zeros after it, times bigger than the gravitational force. However, there are two kinds of electric charges, positive and negative. The force between two positive charges is repulsive, as is the force between two negative charges. But the force is attractive between a positive and a negative charge. A large body such as the Earth or the Sun contains nearly equal numbers of positive and negative charges. Thus the attractive and repulsive forces between the individual particles nearly cancel each other out, and there is very little net electromagnetic force. However, on the small scale of the atoms and the molecules, the electromagnetic force dominate. The electromagnetic attraction between the negatively charged particles and positively charged protons in the nucleus cause the electron to orbit around the nucleus of the atom. Just as gravitation, the electromagnetic attraction is pictured as being caused by the exchange of large number of virtual massless particles of spin 1 called photons. Again, the photons that are exchanged are virtual particles. However, when an electron changes from one allowed orbit to another, one nearer to the nucleus, energy is released and a real photon is emitted, which can be observed as visible light by the human eye, if it has the right wavelength, or by a photon detector such as a photographic film. Equally, if a real photon collides with an atom, it may move an electron from an orbit near the nucleus to one farther away. This uses the energy of the photon, so it is absorbed. The third category is called the weak nuclear force, which is responsible for radioactivity and which acts on all matter particle of spin half, but not on particle of spin 0, 1 or 2, such as photon and gravitons. The weak nuclear force was not well understood until 1967, when Abdus Salam at the Imperial College London and Stephen Weinberg at Harvard both proposed theories that unified this interaction with the electromagnetic force. Just as Maxwell had unified electricity and magnetism about 100 years earlier, they suggested that in addition to the photon, there were three other spin 1 particles known collectively as massive vector bosons that carried the weak force. These were called omega plus, omega minus, Z naught, and each had a mass of around 100 giga-electron volt. The Weinberg-Salam theory exhibits a property known as spontaneous symmetry breaking. This means that what appears to be a number of completely different particles at low energies are in fact found to be all the same type of particle, only in different states. At high energies, all these particles behave similarly. The effect is rather like the behavior of a roulette ball on a roulette wheel. At high energies, when the wheel is spun quickly, the ball behaves in essentially only one way. It rolls round and round. But as the wheel slows, the energy of the ball decreases and eventually the ball drops into one of the 37 slots in the wheel. In other words, at low energies, there are 37 different states in which the ball can exist. If, for some reason, we could only observe the ball at low energies, we could then think that there were 37 different types of ball. In the Weinberg-Salam theory, at energies much greater than 100 giga-electron volt, the three new particles and the photons would all behave in a similar manner. But at the lower particle energies that occur in the most normal situations, this symmetry between the particles would be broken. Omega plus, omega minus, and Z naught would acquire large masses, making the forces they carry have a very short range. At the time that Salam and Weinberg proposed this theory, few people believed them, and particle accelerators were not powerful enough to reach the energies of 100 giga-electron volt required to produce real omega plus and omega minus or Z naught particles. However, over the next 10 years or so, the other predictions of the theory at lower energies agreed so well with the experiment that in 1979, Salam and Weinberg were awarded the Nobel Prize for Physics, together with Sheldon Glashow at Harvard, who had suggested similar unified theories of the electromagnetic and weak nuclear forces. The Nobel Committee was spared the embarrassment of having made a mistake by the discovery in 1983 at CERN, European Centre for Nuclear Research, of the three massive patterns of the photon with the correct predicted masses and other properties. Carlo Robbia, who led the team of several hundred physicists that made the discovery, received the Nobel Prize in 1984, along with Simon van der Meer, the CERN engineer who developed the antimatter storage system employed. It is very difficult to make a mark in experimental physics these days unless you are already at the top. The fourth category is the strong nuclear force, which holds the quarks together in the proton and neutron and holds the proton and neutron together in the nucleus of an atom. It is believed that this force is carried by another spin-1 particle called the gluon, which interacts only with itself with the quarks. The strong nuclear force has a curious property called confinement. It always binds particles together into combinations that have no color. One cannot have a single quark on its own because it would have a color, red, green, or blue. Instead, a red quark has to be joined to a green and a blue quark by a string of gluons. Red plus green plus blue equals white. Such a triplet constitutes a proton or a neutron. Another possibility is a pair of consisting of quarks and an antiquark. Red plus anti-red, or green plus anti-green, or blue plus anti-blue equals white. Such combinations make up the particles known as mesons. which are unstable because the quarks and antiquark can annihilate each other, producing electron and other particles. Similarly, confinement prevents one having a single gluon on its own, because gluons also have color. Instead, one has to have a collection of gluons whose color add up to white. Such a collection forms an unstable particle called a glue ball. The fact that confinement prevents one from observing an isolated quark or gluon might seem to make the whole notion of quarks and gluons as particles somewhat metaphysical. However, there is another property of the strong nuclear force called asymptotic freedom that makes the concept of quarks and gluons well defined. At normal energies, the strong nuclear force is indeed strong and it binds the quarks tightly together. However, the experiments with large particle accelerators indicate that at high energies, the strong force becomes much weaker and the quark and gluon behave almost like free particles. The success of the unification of the electromagnetic and the weak nuclear forces led to a number of attempts to combine these two forces with the strong nuclear force into what is called the Grand Unified Theory, GUT. This title is rather an exaggeration. The resultant theories are not all that grand, nor are they fully unified, as they do not include gravity, nor are they really complete theories, because they contain a number of parameters whose values cannot be predicted from the theories but have to be chosen to fit in with experiment. Nevertheless, they may be a step towards a complete, fully unified theory. The basic idea of GOTs is as follows. As was mentioned above, the strong nuclear forces gets weaker at high energies. On the other hand, the electromagnetic and weak forces, which are not asymptotically free, get stronger at high energies. At some high energy called the Grand Unified Theory, these three forces would all have the same strength and so could just be different aspects of a single force. The GUTs also predict that at high energy the different spin half-matter particles like quark and electron would also all be essentially the same, thus achieving another unification. The value of grand unified energy is not very well known, but it would probably have to be at least 1,000 million giga electron volt. The present generation of particles, 100 giga electron volt, and machines are planned that would raise this to a few thousand giga electron volt. But a machine that was powerful enough to accelerate particles to the grand unified theory would have to be as big as the solar system, and would be unlikely to be founded in the present economic climate. This is impossible to test grand unified theories directly in the laboratory. However, just as in the case of electromagnetic and weak unified theory, there are low energy consequences of the theory that can be tested. The most interesting of these is the prediction that protons, which make up much of the mass of the ordinary matter, can spontaneously decay into lighter particles such as anti-electrons. The reason this is possible is that at the grand unified energy there is no essential difference between a quark and an anti-electron. The three quarks inside a proton normally do not have enough energy to change into anti-electron, but very occasionally one of them may acquire sufficient energy to make the transition. Between the uncertainty principle means that the energy of the quark inside the proton cannot be fixed exactly. The proton would then decay. The probability of a quark gaining sufficient energy is so low that one is likely to have to wait at least a million years, 1 followed by 30 zeros. This is much longer than the time since the Big Bang, which is a mere 10,000 million years or so, 1 followed by 10 zeros. Thus, one might think that the possibility of spontaneous proton decay could not be tested experimentally. However, one can increase one's chances of detecting a decay by observing a large amount of matter containing a very large number of protons. If, for example, one observed a number of protons equal to 1 followed by 30 zeros for a period of 1 year, one would expect, according to the simplest GOT, to observe more than 1 proton decay. A number of such experiments have been carried out, but none have yielded definite evidence of proton or neutron decay. One experiment used either 1,000 tons of water and was performed in the molten salt mine in Ohio to avoid other events taking place caused by the cosmic rays that might be confused with photon decay. Since no spontaneous proton decay had been observed during the experiment, one can calculate that the probable life of the proton must be greater than 10 million years, 1 with 31 zeros. This is longer than the lifetime predicted by the simplest grand unified theory. But there are more elaborate theories in which the predicted lifetimes are longer. Still, more sensitive experiments involving even larger quantities of matter will be needed to test them. Even though it is very difficult to observe spontaneous proton decay, it may be that our very existence is a consequence of the reverse process, the production of protons, or more simply of quarks, from an initial situation in which there were no more quarks than antiquarks, which is the most natural way to imagine the universe starting out. Matter on the Earth is made up of mainly of protons and neutrons, which in turn are made up of quarks. There are no antiprotons and antineutrons made up from antiquarks except for a few that physicists produced in large particle accelerators. We have evidence from cosmic rays that the same is true for all the matter in our galaxy. There are no antiprotons or antineutrons apart from a small number that are produced as particle-antiparticle pair in high-energy collisions. If there were large regions of antimatter in our galaxy, we would expect to observe large quantities of radiation from the borders between the regions of the matter and antimatter, where many particles would be colliding with their antiparticles, annihilating each other and giving off high-energy radiations. We have no direct evidence as to whether the matter is the matter in our galaxies is made up of protons and neutrons or antiprotons and antineutrons, but it must be one or the other. There cannot be mixture in a single galaxy, because in that case we would again observe a lot of radiation from annihilations. We therefore believe that all galaxies are composed of quarks rather than antiquarks. It seems impossible that some galaxies should be matter and some antimatter. Why should there be so many more quarks than antiquarks? Why are there not equal number of each? It is certainly fortunate for us that the number are unequal, because if they had been the same, nearly all the quarks and antiquarks would have annihilated each other in the early universe and left a universe filled with radiations, but hardly any matter. there would then have been no galaxies, stars, or planets on which human life could have developed. Luckily, grand unified theory may provide an explanation of why the universe should now contain more quarks than antiquarks, even if it started out with equal numbers of each. As we have seen, GUTs allow quarks to change into anti-electron or high energy. They also allow the reverse process, antiquarks turning into electrons and electrons and anti-electrons turning into quarks and antiquarks. There was a time in the very early universe when it was so hot that the particle energies would have been high enough for these transformations to take place. But why should that lead to more quarks than antiquarks? The reason is that the laws of physics are not quite the same for particles and antiparticles. Up to 1956, it was believed that the laws of physics obeyed each of the three separate symmetries called C, P, and T. The symmetry C means that the laws are same for particles and antiparticles. The symmetry P means that laws are the same for any situation and its mirror image. The mirror image of a particle spinning in a right-handed direction is one spinning in a left-handed direction. The symmetry T means that if you reverse the direction of motion of all particles and antiparticles, the system should go back to what it was at earlier times. In other words, the laws are the same in 1965, two American physicists, Sang-Dao Lee and Chang-Ning Yang, suggested that the weak forces does not in fact obey the symmetry P. In other words, the weak forces would make the universe develop in a different way from the way in which the mirror image of the universe would develop. The same year, a colleague, Xian Wu, proved their prediction correct. She did this by lining up the nuclei of radioactive atoms in a magnetic field so that they were all spinning in the same direction, and showed that the electrons were given off more in one direction than another. The following year, Lee and Young received the Nobel Prize for their idea. It was also found that the weak forces did not obey the symmetry C, that is, it would cause a universe composed of antiparticles to behave differently from our universe. Nevertheless, it seemed that the weak forces did obey the combined symmetry C-P. That is, the universe would develop in the same way as its mirror image. In addition, every particle was swamped with its antiparticle. However, in 1964, two more Americans, J.W. Cronin and Wal Fitch, discovered that even the CP symmetry was not obeyed in the decay of certain particles called K-mesons. Cronin and Fitch eventually received the Nobel Prize for their work in 1980. A lot of prizes have been awarded for showing that the universe is not as simple as we might have thought. There is a mathematical theorem that says that any theory that obeys quantum mechanics and relativity must obey the combined symmetry CPT. In other words, the universe would have to behave the same if one replaced particles by antiparticles, took the mirror image, and also reversed the direction of time. But Cronin and Fitch showed that if one replaces particle by antiparticle and takes the mirror image but does not reverse the direction of time, then the universe does not behave the same. The laws of physics, therefore, must change if one reverses the direction of time. They do not obey the symmetry T. The early universe does not obey the symmetry T. As time runs forward, the universe expands. If it ran backward, the universe would be contracting. And since there are forces that do not obey the symmetry T, it follows that as the universe expands, these forces could cause more anti-electrons to turn into quarks than electrons into anti-quarks. Then as the universe expanded and cooled, the anti-quarks would annihilate with the quarks, but Since there would be no quarks, then antiquarks, a small axis of quarks would remain. It is these that make up the matter we see today and out of which we ourselves are made. Thus, our very existence could be regarded as a confirmation of grand unified theories, though a qualitative one only. The uncertainties are such that one cannot predict the numbers of quarks that will be left after the annihilation, or even whether it would be quarks or antiquarks that would remain. Had it been an axis of antiquarks, however, we would simply have named antiquarks quarks and quarks antiquarks. Grand unified theories do not include the force of gravity. This does not matter too much, because gravity is such a weak force that its effects can usually be neglected when we were dealing with elementary particles or atoms. However, the fact that it is both long-range and always attractive means that its effects all add up. So, for a sufficiently large number of matter particles, gravitational forces can dominate over all other forces. This is why it is gravity that determines the evolution of the universe. Even for objects and the size of stars, the attractive force of gravity can win over all the other forces and cause the stars to collapse. My work in the 1970s focused on the black holes that can result from such stellar collapse and the intense gravitational field around them. It was this that led to the first hints of how the theories of quantum mechanics and general relativity might affect each other, a glimpse of the shape of quantum theory of gravity yet to come. Thank you very much for watching. See you in the next chapter. Thank you very much for watching. If you want some more videos like this one, please like, share and subscribe to my channel. Have a great day. Stay home. Stay safe.